Well, last time we discussed about acid-base catalysis, that is homogeneous catalysis. Okay. Now today let us see variation of rate of reaction. Variation of rate of reaction. Rate of reaction, that is rate constant. That is rate constant. A rate constant with pH. With pH. Let us see this. Okay, let us see this. So, how the rate constant or rate of reaction varies as the pH of the medium changes. Okay, pH changes means it may be acidic, it may be basic, or it may be neutral, like that. Okay. Now, last time we have seen that um, specific acid catalysis rate constant for specific acid catalysis is given by this, general acid catalysis is given by this, and specific base catalysis is given by this, and general base catalysis is given by this. Okay. Now suppose the reaction is catalyzed by hydronium ion and hydroxide ion at the same time. Suppose. Okay, I repeat. Suppose the reaction is catalyzed by hydronium ion and hydroxide ion at the same time. That means specific acid catalysis and specific base catalysis at the same time. Suppose, say, in that case, K will be equal to K naught, okay, K naught uncatalyzed, then KH3O plus catalytic constant, then it will be KOH minus and this minus. Okay, so by this we mean that the reaction is catalyzed by hydronium ion, that is acid, and base, hydroxide ion base at the same time. Okay, but this is highly improbable. It is highly improbable that the reaction will be catalyzed at the same time by acid and bases. Okay, for example, suppose we are taking say 1 molar HCl. If we take 1 molar HCl solution, suppose reaction is catalyzed by 1 molar HCl solution. I repeat, suppose the reaction is catalyzed by 1 molar HCl solution. In that case, the reaction will be catalyzed only by hydronium ion, not by hydroxide ion. Okay. Similarly, if we take say 0.1 molar sodium hydroxide solution, say reaction is catalyzed by 0.1 molar sodium hydroxide solution. In that case, the reaction will be catalyzed by hydroxide ion only, not this, not hydronium ion. Therefore, it is highly improbable that a reaction will be catalyzed by both hydronium ion and both hydroxide ion at the same time. Okay. Still we can consider the various possibilities. Still we can consider the various possibilities how the reaction is catalyzed by acids and bases. Okay, and that was done by one scientist called Scrabble. Okay, Scrabble. Okay, so he actually, what he did is that he plotted log K versus pH. He plotted log K versus pH to discuss about the variation of rate constant with pH of the medium. Okay. Now let us take one example. Suppose the reaction is catalyzed by only hydronium ion. Okay, only hydronium ion. In that case, K will be equal to K naught plus KH3O plus N this. Okay, this. If we take log, so log K, that will be equal to log K naught plus log of M into N equal to log M plus log N. Okay, we get this. Or so this is constant, so I can write this as C. What is C? This plus this, constant. C is a constant which is equal to this constant. Okay, then I can write it like this, so minus log of hydronium ion concentration. I can write it like this, and this is nothing but C minus pH. Okay, that means log K equal to this. Okay, now suppose this is y equal to mx plus c. It is like this. Therefore, if we draw a graph between log K and pH, now here m, value of m is -1. If we draw graph between log K and pH, in that case value of m will be -1. That means slope is -1. Okay, so in that case our graph will be like this. Okay, in that case, say I am plotting this. In that case the graph will be like this. Okay, so this is pH, and this is log K. Okay, log K. So m is negative, so basically this is the equation of a straight line, y equal to mx plus c. This is the equation of a straight line. But since m is negative, the graph will be like this. Okay, graph will be like this. That means if the reaction is catalyzed by hydronium ion only, specific acid catalysis. So you see, as pH increases, rate of reaction decreases. Log K decreases, that means rate constant decreases, that means rate of reaction decreases. Okay, so we get this. Now say the reaction is catalyzed by base only, hydroxide ion. In that case, K will be equal to K naught plus KOH minus NOH minus. Okay, specific base catalysis. Okay, reaction is catalyzed by hydroxide ion. This is specific base catalysis. This I can write like this. We know that hydronium ion, concentration of hydronium ion, concentration of hydroxide ion, that is equal to Kw, ionic product of water. Kw, ionic product of water. Okay, so for OH we can write Kw divided by H3O. So this is equal to K naught KOH minus KW by H3O plus. Okay. Now if we take log, that will be log K naught plus log KOH minus, okay, log KOH minus plus log KW, this will be minus log H3O plus, minus log H3O plus. Once again, constant. So I can write this as say C dash. Constant. So I can write this plus this equal to C dash. So this is plus minus log of hydronium ion concentration. Okay. And that is equal to C dash plus pH. Okay. Now once again, if we plot, this is Y mx plus C. So we will get a straight line. Okay. We will get a straight line. We will get a straight line like this. But here m is slope. Slope is positive. So our straight line will be like this. Straight line will be like this. Straight line will be like this. Because m is positive, so straight line will be this. Okay, this is specific base catalysis. Okay, now suppose reaction is catalyzed by both. Okay, if say uncatalyzed reaction is also present, then we will get this horizontal portion. Okay, we will get this. So this is in general, say K, say reaction is both catalyzed by hydrogen ion and hydroxide ion. Okay, hydroxide ion. So this is equal to K naught plus log and this is KH3O plus H3O plus, and this I can write like OH minus KW H3O plus. Okay, H3O plus. So this is when the reaction is catalyzed by both hydronium ion and hydroxide ion. Okay, in that case the graph will be like this. Okay, the reaction is catalyzed by both hydronium ion and hydroxide ion. The graph is like this. This is catalyzed by acid, this is catalyzed by base hydroxide ion, and this is uncatalyzed reaction. Now, as we have discussed, if the reaction is catalyzed by only hydronium ion, there is no uncatalyzed reaction, then the graph will be like this. Only this portion means the reaction is catalyzed by hydronium ion. There is no uncatalyzed reaction. But if uncatalyzed reaction is also present, the graph will be like this. If uncatalyzed reaction is also present, the graph will be like this. So this graph is for uncatalyzed reaction, this is for acid catalyzed reaction. Okay, that means hydronium ion catalyzed reaction, acid catalyzed reaction. Similarly, if the reaction is catalyzed by only base, the graph will be this. And if this is catalyzed by hydroxide ion only, there is no uncatalyzed reaction. If the reaction is catalyzed by hydroxide ion and uncatalyzed reaction is also there, then the graph will be like this. Okay? But if the reaction is catalyzed by acid, hydronium ion, and catalyzed by base, but there is no uncatalyzed reaction, suppose. There is no uncatalyzed reaction. In that case, the graph will be like this. This graph means horizontal portion is absent. That means catalyzed by acid, catalyzed by base, there is no uncatalyzed reaction. So these are the various possibilities. As discussed by Scrabble. Okay? এনেকুৱা ধৰণে বিভিন্ন পসিবিলিটি হ'ব পাৰে য'ত ৰিয়েকশ্যনটো এচিড বা বেছৰ দ্বাৰা কেটালাইসিস হয় okay so this is all about variation of the reaction with pH now let us discuss about enzyme catalysis So enzyme catalysis, okay. So you know, in our body, so many reactions are going on, okay, and almost all the reactions take place in presence of enzymes, and enzymes are the catalysts, and not only in our body. So in case of any living organism, so many reactions are going on, and most of these reactions are catalyzed by enzymes. Okay, so enzymes increase the rate of reaction to a large extent. Okay, now you know about lock and key model. So for enzyme action, there is one model called lock and key model. What does it mean? You know, for a particular lock, we have a particular key. That key cannot be applied to other lock. Okay? So for one lock, there is one specific key. Okay? এটা তলাৰ কাৰণে আমাৰ এপাত চাবি থাকিব সেই চাবিপাত আমি বেলেগ তলাত ব্যৱহাৰ কৰিব নোৱাৰো okay ঠিক তেনেকৈ if you think the lock to be the enzyme and key to be the substrate means reactant okay reactant so for a particular lock, we have a particular key. That means for a particular enzyme, we have a particular substrate. Okay? One particular substrate is catalyzed by one particular enzyme. Therefore, we say that action of enzyme is highly specific. highly specific, because one particular reaction is catalyzed by only one enzyme. Okay. Now, what is the mechanism of enzyme catalyzed reaction? What is the mechanism of enzyme catalyzed reaction? And the mechanism of enzyme catalyzed reaction was given by Leonard Michaelis and Maud Menton. Chaelis. Leonard Michaelis and Michaelis. Okay. Michaelis. Leonard Michaelis and Maud Menton. So mechanism of enzyme catalyzed reaction was given by Michaelis and Menton in 1913. And what is the mechanism? So step 1, in the mechanism, the enzyme, first step in the mechanism is this: enzyme reacts with the substrate, that is reactant. Okay, this is a reversible reaction. K1 K minus 1, and we get, yes, that is called enzyme substrate complex. Enzyme substrate complex. Okay, this is the first step of the mechanism. And what is the second step? Second step is that this enzyme substrate complex, it breaks down to form the product, and of course we get back the catalyst, that is enzyme. P is the product. We get the product and we get back the catalyst, that is enzyme. Okay. So this is the mechanism proposed by Michaelis and Menton. Okay. Here, this is the slowest step. This is the slowest step. And this is fast reaction. Okay. Fast reaction means K1 and K minus 1 is very, very greater than K2. Okay. This is very, very greater than this. This is very, very greater than this, because this is fast reaction, this is slow reaction. Okay. That means first the enzyme and the substrate forms this complex. Okay. Then this substrate is converted to the product. Okay. And while bound to the enzyme, this substrate is converted to the product. মানে এনজাইমটোৰ লগত বাইণ্ড হৈ থাকোঁতেই কি হয়, ছাবষ্ট্ৰেটটো প্ৰডাক্টলৈ কনভাৰ্ট হয়, and the enzyme gets released. Okay. So this is the mechanism proposed by Michaelis and Menton. Okay. Now you see what is the overall reaction? Overall reaction we can write like this. Overall reaction is substrate is converted to product, because you see cancels, so substrate is converted to product. So this is the overall reaction. Okay, so from this rate of reaction, equal to minus ds by dt equal to dp by dt. And you know, this is the definition. This is the definition of rate of reaction. Okay, so according to definition, the rate of reaction is this. Okay, now generally what happens? Generally what happens? Generally what happens? Concentration of enzyme is much less than the concentration of the substrate. Enzyme is present to a very small amount. Normally that is the case. Amount of enzyme is very less, but obviously amount of the substrate will be much higher. So this is the normal case. Okay, since this is less, since concentration of enzyme is less, okay, concentration of enzyme is less, so concentration of enzyme substrate complex will also be less. That means so concentration of enzyme substrate complex is very less than this. Because this is less, obviously concentration of this will be less. Okay, now here this is the slowest step, second step is the slowest step, and this is the rate determining step. Okay, so this is the rate determining step. So from step 2 what we can write? From step 2 what we can write? You see, what is rate of reaction? Rate of reaction equal to this. Okay, so from step 2, r equal to dp by dt, dp by dt rate of the reaction, and that must be equal to k2 es, concentration of es. Okay, so this is a number 1 equation. This is number 1 equation. Now you see, now from these three mechanisms, from these three steps, if we write des by dt, so now you can write this. You have already learned how to write this. Okay, from these three steps we have to write des by dt. Since here we have this. Okay, in the rate expression we have concentration of es, enzyme substrate complex. Therefore we will write des dt from these mechanisms. Okay, so what we get? We will get k1 concentration of E, concentration of S. Okay, then minus k minus 1 concentration of ES, then minus k2 concentration of ES. So you know this already. Okay, now this is enzyme substrate complex. Enzyme substrate complex is an intermediate. Enzyme substrate complex is an intermediate. Okay, so according to steady state approximation, what we get? Des by dt equal to 0. Okay, so this is equal to 0. So k1 es minus k minus 1 es minus k2 es. Es equal to 0. Okay, according to steady state approximation. Or we can write like this, K1 Es minus, I can take Es common, so K minus 1 plus K2 concentration of Es. Okay, concentration of Es. So this is the equation number 2. This is equation number 2. This is equal to 0. Sorry, this is equal to 0. Equation number 2. Okay. Now here you see uh, concentration of enzyme. Concentration of enzyme is generally less. Okay, but here you see, what does this mean? Here, what does this mean? Okay, what does this mean? This means concentration of enzyme remaining. This means concentration of enzyme remaining after reacting with the substrate. Okay, in this reaction what happens? This means this is the concentration of enzyme remaining after reacting with this to form this enzyme to a substrate লগত. Suppose initially we have, say, initial concentration of enzyme. Okay, say initial concentration of enzyme say this is equal to E naught. Okay, now some of these have reacted with the substrate to form enzyme substrate complex. Okay, that means initial concentration was this. Out of that, some have reacted to form this complex. Okay, so how much remaining? This is the remaining concentration. This is the remaining concentration of the enzyme. Okay, because initially this much enzyme was present. Out of that, some of the enzyme have reacted with the substrate to form the complex. So what is the concentration of unreacted enzyme? This minus this concentration of unreacted enzyme. Okay, therefore from 2 what we can write? From 2 for this. Okay, for this I can write this. Okay, so I can write this K1 E naught minus ES equal to K minus 1 plus K2 concentration of enzyme substrate complex. Hence, what is the concentration of enzyme substrate complex? Concentration of enzyme substrate complex equal to K1 E naught minus ES divided by K minus 1 plus K2. Okay, K minus 1 plus K2. Okay, or we can write it like this. I could have done something else. Let me write it like this. Okay, let me write it like this. Here we have ES. Okay, here we have ES, so uh, this into S. Okay, for E I am writing this, for E I am writing this, then we have this, so I can write it like this: K1 E naught S, K1 E naught S minus K1 E S equal to K minus 1 plus K2 ES. Okay, now this ES is here, so I will bring it here. Okay, or K1 E naught S, this is equal to, so here, so this will be equal to K minus 1 plus K2 plus K1S plus K1S whole ES. So we get this. Okay, so we get this. Therefore, concentration of ES equal to K1 E naught S divided by K1S plus K minus 1 plus K2. Okay, we are getting this. So what is the rate of the reaction? You see, what is the rate of the reaction? Rate of the reaction equal to K2ES. That is equation number 1. And we are finding out the value of ES. We are finding out the value of ES. Okay. So we are getting the value of ES. Okay. So hence from 1, equation 1, what will be the rate of the reaction? What will be the rate of the reaction? That is equal to K2ES. K2ES. And that will be equal to, so K2, K1 E naught S, K1S plus K minus 1 plus K2. Okay, this. Now we can, and this is K2, this is K2, K1, K2. Okay. Now we can divide numerator and denominator by K1. Okay, we can divide denominator and numerator by K1. So if we divide this, what we get? We will get K2 E naught S, then S, and this will be K1, K minus 1 plus K2 divided by K1. Okay. Now this thing, K minus 1 plus K2 divided by K1, that is called Michaelis constant. Michaelis constant. And it will be represented like Km. Michaelis constant. This is Michaelis. Okay. So we can write, hence we can write R equal to K2 E naught S plus Km. Okay. Now this is known as the Michaelis-Menten equation. This is known as Michaelis-Menten equation. Michaelis-Menten equation for enzyme catalysis. Now here we can consider some cases. We can consider some cases. Suppose when all the enzyme react with the substrate, react completely with substrate, substrate, okay. So what was the initial concentration of enzyme? Initial concentration of enzyme was E naught. E naught. So all the enzyme have reacted with the substrate. Okay. In that case, what will happen? Concentration of E naught will be equal to this, because when all the enzyme react with this substrate, there will be no unreacted enzyme. Okay, when all the enzyme reacts with the substrate, there will not be unreacted enzyme. That means this will be 0. This is 0 means this is equal to this. Okay, so we get this. So in that case what happens? In that case, so from 1, okay, from 1. So from 1, what we get? R equal to K2ES, R equal to K2ES. So this will be equal to K2ES, and that will be equal to K2E naught. And that we generally write as R naught. Okay, say this is equation number 3. Okay, this is equation number 3. Hence from 3 what we get? So from 3 what we get? R equal to K2E naught. For that I can write R naught S plus Km. So we get this. Okay, Km. So let me write it capital K. Okay, let me write it capital K. Michaelis constant. Let me write it capital K. Michaelis constant. Okay, let me write once again. R naught S plus Km. Michaelis constant. Okay, this is the equation number 4. This is equation number 4. Okay, now you see we can again consider some cases. What are those cases? Say case 1. So we can consider some cases. Suppose case 1. Okay, say at low concentration of the substrate. That means when concentration of the substrate is very low. Okay, that is such that concentration of substrate is very less than Km. So substrate concentration is very less. So that means this is very very less than Km. Okay, in that case what we can write from 4? So from 4 what we can write? What we can write? R equal to, we can neglect the concentration of substrate. Okay, we can neglect the concentration of substrate. That means it will be equal to R naught S by Km. Okay, R naught S by Km, or what is R naught? What is R naught? R naught equal to K2 E naught. K2 E naught. K2 E naught by Km S. Because what is R naught? R naught equal to K2 E naught. K2 E naught. Okay, so we can write this. Now that means the reaction is first order. So reaction is first order. Is first order with respect to substrate. With respect to substrate. Okay, with respect to substrate. But another case we can consider, case 2. Another case we can consider, at high concentration of substrate. At high concentration of substrate. Such that substrate constant is very very higher than this. Okay, so in that case we can neglect Km. In that case we can neglect Km. So in that case, from 4 again, from 4 what we get? R equal to, now this is R naught S divided by S. That means this is equal to R naught. Okay, that means this is equal to K2 E naught. That means this reaction is zero order with respect to substrate. So we are getting two conditions. According to one condition, the enzyme substrate reaction is first order with respect to substrate. Okay, when substrate concentration is small. Okay, the reaction will be first order with respect to the substrate when substrate concentration is small. But when substrate concentration is very high, in that case the reaction will be zero order. So graphically we can show like this. Show like this. Okay, so here we are plotting rate of the reaction, and here concentration of substrate. The graph will be like this. Okay, now here you see this is rate of the reaction is independent of substrate concentration. Here after this point what happens? After this substrate concentration, rate of the reaction is independent of the substrate concentration, because it is going parallel. Okay, so above high concentration of substrate, the reaction is of zero order. That means it is independent of the concentration of the substrate. But here you see, as substrate concentration increases, rate of reaction increases. This portion, as substrate concentration increases, rate of reaction increases. This is first order reaction. But here, after this, substrate concentration increases, but rate of reaction is constant. That means rate of reaction is independent of the substrate concentration. That is zero order reaction. Okay. Now third condition is that say if Km is equal to substrate concentration. Okay, in that case R will be from 4 R will be equal to what? You see, this is equal to this, so what we can write? This plus S, we can write S plus S, that is 2S. So what we can write? R naught S 2S, we can write this, and that is equal to R naught by 2. And this is R naught. Okay, this is R naught. Maximum rate. This is the R naught, maximum rate. Okay, this is the maximum rate. You see, R naught. So R naught by 2 means this. This is R naught by 2. Okay, and this is first order reaction. First order, and this is zero order reaction. And here you see R naught by 2, that means here at this point concentration of substrate equal to Km. At this point concentration of substrate equal to Km at this point. So we get this kind. So then we have to discuss about one point, which is called turnover number. Here actually the constant K2 is called the turnover number of the enzyme. What it actually means? Actually, it is defined as the number of molecules of substrate converted per unit time by one molecule of the enzyme. Okay. So what is turnover number? It is the number of molecules, number of substrate molecules converted to product by one molecule of enzyme, per unit time. Okay, so this is turnover number. Okay, and turnover number, that is also called catalytic constant. Catalytic constant of the enzyme. Okay, Now, number of substrate molecules converted to product by one molecule. এনজাইমৰ এটা মলিকিউলে 1 সেকেন্ডত সাপোজ এনজাইমৰ এটা মলিকিউলে 1 সেকেন্ডত কিমানটা সাবস্ট্রেট মলিকিউলক প্ৰডাক্টলৈ কনভাৰ্ট কৰিছে দ্যাট ইজ দি টাৰ্নঅভাৰ নাম্বাৰ আই ৰিপিট এনজাইমৰ এটা মলিকিউলে 1 সেকেন্ডত কিমানটা সাবস্ট্রেট মলিকিউলক প্ৰডাক্টলৈ কনভাৰ্ট কৰিছে তাৰমানে একচুৱেলি সাইকেলছ কিমানটা ক্যাটালাইটিক সাইকেলছ কমপ্লিট হৈছে পাৰ ইউনিট টাইম আৰু কিমানটা ক্যাটালাইটিক সাইকেলছ মানে টাৰ্নঅভাৰছ কিমানটা টাৰ্নঅভাৰছ হৈছে ওকে গতিকে এনজাইমটোৰ এটা এক্টিভ সাইট থাকিব সেই এক্টিভ সাইটত কি হ'ব সাবস্ট্রেটটোৱে বাইন্ড কৰিব each enzyme has an active site আৰু সেই এক্টিভ সাইটটোত সাবস্ট্রেটে লগ লাগিব বাইন্ড কৰিব ওকে গতিকে এটা এক্টিভ সাইটত এটা এনজাইমৰ এটা এক্টিভ সাইটত 1 সেকেন্ডত কিমানটা ক্যাটালাইটিক সাইকেল দ্যাট ইজ টাৰ্নঅভাৰ কমপ্লিট হৈছে ক্যাটালাইটিক সাইকেল কমপ্লিট হৈছে মানে কিমানটা সাবস্ট্রেটৰ লগত ৰিয়েকশন কৰিছে যিমানটা সাবস্ট্রেটৰ লগত ৰিয়েকশন কৰে সিমানটাই ক্যাটালাইটিক সাইকেল হ'ব ওকে সো নাম্বাৰ অফ সাবস্ট্রেট মলিকিউলস ৰিয়েক্টিং উইথ one catalytic molecule one enzyme molecule in 1 second that will be equal to the number of catalytic cycles or catalytic cycles that is also called turnovers okay so this is turnover number okay now generally value of k lies within the range value of k2 generally lies within the range 100 to 1000 per second তাৰ মানে আমি কি বুজিলো যে 1 সেকেন্ডত এটা এনজাইমে কিমানটা সাবস্ট্রেট মলিকিউলৰ লগত ৰিয়েকশন কৰিব পাৰে from 100 to 1000 তাৰমানে ইমানটা ক্যাটালাইটিক সাইকেল 100 ৰ পৰা 1000 ক্যাটালাইটিক সাইকেল কমপ্লিট কৰিব পাৰ ইউনিট টাইম 1 সেকেন্ডত ইমানটা ক্যাটালাইটিক সাইকেল কমপ্লিট কৰিব অৰ্থাৎ ইমানটা সাবস্ট্রেট মলিকিউলৰ লগত এনজাইমটোৱে ৰিয়েকশন কৰিব বুজিছে নৰমালি এইটো ৰেঞ্জত থাকে কিন্তু কেতিয়াবা এইটো কে দিস মে বি উইদিন দি ৰেঞ্জ 10 to the power 5 to 10 to the power 6 per second so normally k2 lies within this range কিন্তু কেতিয়াবা হ'ব পাৰে কেতিয়াবা ইমানো হ'ব পাৰে so it may be very high okay এতিয়া Michaelis Menten equation কি আছে in the Michaelis Menten equation we have r naught we have km in the Michaelis Menten equation we have r naught and km okay how to find out the values of r naught and km okay how to find out the values of r naught and km and there is one method which is called Lineweaver bark method okay to find out the values of r naught and km Michaelis constant we have a method which is called Lineweaver bark method okay In this method, what is done? Say this equation. Here r equal to this. Okay, I can write from this equation, from equation 3, I can write 1 by r. If I write 1 by r, then this will be divided by this. Okay, let us do that. From equation 3, if I write 1 by r, that will be equal to concentration of S plus Km divided by K2 E naught S. Okay, this I can write like this. Say this divided by this plus this divided by this. So I can write Km by S plus 1 by K2 E naught. Okay, or I can write it like this: Km K2 E naught Km by K2 E naught S plus S cancels, so 1 by K2 E naught. Okay, now we have already seen K2 E naught equal to R naught S plus 1 by R naught. Or I can write it like this: Km by R naught into 1 by S plus 1 by R naught. Okay, so 1 by R equal to this. So 1 by R equal to suppose Y. 1 by R equal to suppose Y. Equal to say M. 1 by S equal to say X and C. So if we draw graph between 1 by R and 1 by S, we will get a straight line with intercept this. So we will get a straight line. Let us see that. 1 by R, 1 by S. Okay. So if we plot this, 1 by R, 1 by R and 1 by S. So we will get a straight line. Like this. Okay. Now this is the intercept. Here, this is the intercept. And intercept equal to 1 by R naught. C is the intercept. C equal to 1 by R naught. So intercept equal to 1 by R naught. So this is equal to 1 by R naught. So if we measure this intercept, suppose, let me write it like this. Say 1 by R naught equal to say Y. 1 by R naught equal to say Y. This is a Y. So from this we get the value of R naught. What is R naught? 1 by Y. We just measure this. এইখিনি আমি জুখিব লাগে, জুখিলে we get the value of Y, so we get the value of R naught. Okay, we get the value of R naught. Then if we take slope of this, if we take slope means there is a y by x. So we can find out the slope of the straight line. Here I am slope লব পাৰো গতে slope to কাৰ সমান হ'ব slope will be equal to km by r naught. Slope will be equal to km by r naught. Okay, now slope. So we can measure the slope. We can measure the slope. Slope will is equal to this. This is a y dash by x dash. So it will be y dash by x dash. Slope equal to tan theta. Slope equal to tan theta, tan theta, y dash by x dash. So we can find out the slope, and that must be equal to km by r naught. That is equal to y dash by x dash. So we have already found out r naught. Okay, r naught or value to আমি পাইছোৱে. So r naught or value to পাইছো, slope পাইছো. By measuring this we get slope. So we get the value of km, Michaelis constant. Okay, so in this way we can find out the value of Michaelis constant. Michaelis constant value to আমি এনেকে উলিয়াব পাৰো. Okay, now what is the significance of Michaelis constant? Significance of Michaelis constant. What is the significance? Now we have already seen that km equal to k minus 1 plus k2 divided by k1. Okay, now we have already seen that this step is the slowest step and this is fast. That means k minus 1 is very greater than k2. Okay, so you see since k minus 1 is greater than k2, so what we can write? So k minus 1 plus k2, that will be approximately equal to k minus 1. That means km equal to k minus 1 by k1. Okay, k minus 1 by k1. Okay, now if you so for this equilibrium we can write equilibrium constant. What is equilibrium constant? Rate constant of the forward direction divided by rate constant of the backward direction. What is equilibrium constant? Rate constant of the forward direction divided by rate constant of the backward direction. Okay, so equilibrium constant for step 1. Equilibrium constant for step 1, that is say k equilibrium constant, and that equal to k1 by k minus 1. Hence you see, so Michaelis constant is equal to 1 by k equilibrium. Okay, so you see here you see, let me write here what is equilibrium constant. K equilibrium constant, that is equal to K1 by K minus 1. Okay, equilibrium constant. If concentration of this is more, then value of equilibrium constant will be more. If concentration of enzyme substrate complex is more, okay, concentration of enzyme substrate complex is more, value of equilibrium constant is more. Conversely, higher the value of equilibrium constant, that means more enzyme substrate is formed. Okay, so enzyme equilibrium constant or value to besi hua mane enzyme substrate complex to basic form hoise. Okay, basic form hoise, tamne ki hoise দুইটাৰ মাজত এফিনিটিটো বেছি, এনজাইম আৰু সাবস্ট্ৰেটৰ মাজত এফিনিটিটো বেছি। ওকে, গতিকে কি হ'ব, দুইটাৰ মাজত এফিনিটিটো বেছি, so more enzyme substrate complex is formed, so value of equilibrium constant is more. Ultimately, equilibrium constant more means affinity between enzyme and substrate is more. I repeat, value of equilibrium constant is more. That means affinity between enzyme and substrate is more. But what is Michaelis-Menten constant? Okay, higher the value of K equilibrium, more is the affinity between enzyme and substrate. গতিকে ইকুইলিব্ৰিয়াম কনষ্টেণ্টৰ ভেলুটো বেছি হোৱা মানে এনজাইম আৰু ছাবষ্ট্ৰেটৰ মাজৰ এফিনিটিটো বেছি। কিন্তু মাইকেলিছ কনষ্টেণ্ট উল্টাটো হ'ব, তাৰমানে হায়াৰ দি ভেলু অফ কে এম মাইকেলিছ কনষ্টেণ্ট, লোৱাৰ উইল বি দি এফিনিটি বিটুইন এনজাইম এণ্ড ছাবষ্ট্ৰেট। So this is the significance of Michaelis constant. Higher the value of Michaelis constant, lower will be the affinity between enzyme and substrate. Conversely, lower is the value of Michaelis constant, higher is the affinity between enzyme and substrate. Okay, so this is all about Michaelis-Menten equation, enzyme catalysis. Okay, so next time we will discuss about catalysis on solid surface. Okay, thank you.